Students, my screen was visible. Good morning. My screen is visible. Anyone?
Yes, sir.
Okay.
Yes, sir.
Okay. Good morning to all the students. Welcome to my lecture number 14. Load test and block rotor test of induction motor. Okay. Today we are going to discuss the testing methods of induction motor. Okay. So before going to the testing methods, we have to know about the concept of equivalent circuit. Equivalent circuit of induction motor. Okay, equivalent circuit. Actually, you know the concept of transformer. Okay, transformer is the static device which transfer electric energy from one stage to another stage. So the induction motor also be act as an rotating transformer. Okay, it is act as an rotating transformer. Now by using the transformer concept, now I'm going to draw an equivalent circuit. Okay, equivalent circuit. We know the induction motor, it's having two parts. Okay, it's having two parts. One is, this is stator. Okay, and another inside there will be a rotor. Okay, inside there will be a rotor. This is the rotor. Okay, between stator to rotor there is a gap. Okay, there is a gap. This dotted line stands for air gap. Okay, air gap. Now this motor will be fixed in the bed. Be fixed in the bed. Okay, by using the bolt and nuts. Okay, now we know the stator will be the stationary member, rotor is a rotating member. Now how the induction motor be act as a transformer? Okay, transformer means it is a rotating transformer. Now in transformer we know the concept. Transformer is a static device which transfer power from or energy from one place to another place, that is left to right, we can transfer it. Now by using the transformer principle, now I'm going to draw the circuit diagram of equivalent circuit. Now in transformer we know there are two windings, one is primary, another one is secondary, like that. Stationary stator will be the primary winding, primary, and rotor is the secondary winding. Okay, secondary winding. Okay, now okay, so in primary winding, okay, in primary winding I am drawing the resistor. Resistor and inductor. Okay, will be connected only in the stator. Okay, this value will be R1, X1, and the voltage we are applying, it is V1. Okay, V1 is the induced voltage. Okay, V1 is the induced voltage. So in primary side there will be a resistor and inductor. Okay, there are two components are flowing it, that is nothing but R0, X0. Okay, R0, X0, excuse me. R naught, X naught. Okay, this side will be primary. Okay, this is primary side, and secondary side I have to draw. Okay, in secondary side actually this is a rotor. Okay, this is a rotor, understand? So in secondary side how to draw? In secondary side there will be resistor, another one is inductor will be connected. Okay, so this is R2, this one will be X2R, and the EMF induced in rotor side which will be E2R. Okay, this R stands for rotating. Okay, this R stands for rotating. So the right hand side I am mentioning it rotating secondary. That's what I am saying. This is rotating transformer. Okay, induction motor is other name called as rotating transformer. Okay, now the symbol of R1. Okay, this R1 stands for stator resistance per phase. I will mention the symbols. R1 stands for stator resistance per phase. Okay, and X1 stands for stator reactance per phase, and R naught. Okay, this one. Okay, then R naught stands for, it is represent no load loss resistance. Okay, the formula for R naught equal to V1 by IC, because in R naught the current flowing here IC. Okay, the current flowing here it will be I mu or Im. Okay, the current flowing in R naught is IC. IC stands for active component current. Okay, so in some textbooks they can mention this IC will be in another notation also. Another one I mu. I mu stands for magnetizing
I will ask sir. We are paying rent and putting the car.
current. Okay, this I mu we can mention the notation called Im also. Okay, Im also. Then X naught. X naught will be the reactance flux setup which is equal to X naught equal to V1 by IM. Okay, Vm by Im. Okay, Vm by Im. Okay, these are the notation. Okay, and X1 is the stator reactance
Nobody is preferring, sir. Everybody left this year. They are saying first we
state. Then E1, because E1 is the EMF
Sir, again it will come out next year.
induced
Next year
in
it will come and people won't again put that. That time this
primary.
competition
Okay,
also will be
EMF induced in the
lesser. Because many
primary.
are going for
Okay,
other businesses.
E1 is the induced voltage in stator per phase. Okay, stator per phase. And E2 stands for rotor induced EMF per phase on standstill. Okay, and K is the transformer ratio. It is transformer ratio is other name called K equal to stator turns by rotor turns, where K is transformer ratio. Okay, transformer ratio. Then E2R. E2R stands for rotor induced EMF per phase in running condition. Okay, in running condition. And X2R is the rotor reactance per phase in running condition. Okay, running condition. Okay, these are the notation. Okay, and here the overall current, when you give the voltage V1, the current flows I1. Okay, this current will meet this junction point. Okay, the current flowing in this component is I naught. Okay, I naught. So I naught equal to active component plus magnetizing component. Okay, now I am drawing the simple equivalent circuit. Okay, in the basic equivalent circuit. Whether the screen is visible, basic equivalent circuit, how to draw. This is R1, X1, V1, you are applying, I1 is flowing, and here R0, X0. So here it is I0. This is my junction point. So this is IC. This point is IM. Okay. This is the gap, R gap. This is mutual coupling. This is R gap. Okay. This is stator. This side will be the rotor. This side will be the rotor. Okay. Now what is the component here in right hand side? R2. Another one This is R2. Okay. In rotor, reactance running in rotor condition. Okay. Rotor reactance running in a running condition is X2R, right? Okay. X2R. Okay. What is the formula for X2R? X2R equal to S into X2. Okay. And the EMF induced in the rotor side is E2R. We already studied E2R. Okay, E2R equal to S into E2. Okay, and this reactance will be the load. Okay, reactance will be the load. Understand or not? So the current flowing in this rotor, it will be I2R. Okay, I2R. Okay, now the formula for I2R, what is the current formula I2R? I2R equal to E2R by Z2R. So E2R we already know, yes, E2 by square root of R2 square plus S X2 whole square. Okay, S X2 whole square. Again we can write this equation in another form, E2 by square root of R2 by S whole square plus X2 square. Okay, we can write in this form also. Okay, now if you take this rotor side, okay, now we have to consider, because stator we should not disturb. Okay, rotor we are going to apply the load. Okay, this rotor side only we have to apply the load, then only we can measure the speed and torque. Okay, so this circuit I will draw separately. Okay, the rotor circuit. Rotor equivalent circuit I will draw separately. What is a rotor equivalent circuit? Which it denotes E2R, R2, X2R. Okay, that I will draw it here separately. R2 okay, this is R2, this one is reactance X2R. X2R is, what is the formula for X2R? S into X2. Okay, and this is E2R. E2R, and the current flowing here, because it is closed loop, okay, it is I2R. Okay, so now we already know E2R equal to S into E2. Okay, now instead of this E2R, because in primary side it is E1, okay, in secondary side also we have to represent E2, but rotor is running. So because of this rotor is running, what happened? It is E2R is coming. Okay, now you are going to stop the motor. Okay, you are giving the supply, but the motor should not run, because you are applying the load, the motor should not run. So at that time what happened, this notation, when the motor is not in running condition, it comes to E2. Okay, it is E2. Okay, because E2R is the rotor induced EMF at running condition. Okay, when the motor is at it's not running, what happened to my E2 induced EMF? It is E2. Okay, it is E2. When the motor is not in running condition, the notation we have to represent E2. Okay, if I mention E2, okay, what happened? What happened to this notations? To this, okay, R2 will be same in both sides. The R2 will be same. So I have to mention this R2, you omit it. Then this X2, okay, X2 will be removed as X2, because S and S will be cancelled. Okay, because E2R equal to S into E2. Okay, so if you remove this, because this S goes to denominator, you have to divide the S in all the parameters R2 and X2. Okay, when the motor is in standstill, you have to divide the slip value for resistance and reactance. So S and S will be cancelled, so you will get only X2. Reactance, you will get, okay, the reactance you will get R2 by S. Okay, R2 by S. Okay, now the resistance we are varying it. Okay, R2 by S. Okay, now now this is I2 R. Okay, now R2 by S, we can write it as R2 plus R2 by S minus R2. Okay, so R2 plus, take R2 separately, 1 by S minus 1. Okay, 1 by S minus 1. So we will get R2 plus R2 into 1 minus S by S. Okay, again we are going to draw this diagram. Okay, this diagram. X2 E2, this is R2. Okay, this is my first R2, then another R2 will be R2 into 1 minus S by S. Okay, this term, let's call it as load or L. Okay, RL is the load resistance. Okay, RL equal to, RL is the load resistance. So R2 plus RL. Okay, RL is the load resistance. Load resistance means we can use any type of loads, that is a refrigerator or TV or whatever it may be. Load resistance symbol is RL. R2 into 1 minus S by S. Okay, 1 minus S by S. Now by using the transformer ratio, we know the transformer ratio K equal to E2 by E1. Okay, E2 by E1. Okay, now you have to transfer the variables from stator to rotor side. Okay, that's what we are getting that equation. Now you want to transfer rotor to stator side. What happened? Okay, equivalent circuit referred to stator. Equivalent circuit referred to stator. Okay, this is one 3-mark question. In your examination, if I ask sketch the equivalent circuit referred to stator of an induction motor, means you have to draw this diagram. R1 X1. Okay, the combination of R1 X1 is impedance Z1. So here you are applying V1, this is I1. Okay, and this is my junction point, I0, R0, X0, IC, IM. Okay, and this point will be E2 dash. Okay, E2 dash is the notation which we are using for transferring the variables from rotor to stator side. Okay, E2 dash is equal to E2 by K square. Okay, E2 by K square. X2 dash. Okay, X2 dash is nothing but X2 by K square. R2 dash. R2 dash is R2 by K square. Then this is the load. Okay, this is the load. R2 RL dash. Okay, RL dash is equal to R2 dash into 1 minus S by S. Okay, so here only the current flows I2R dash. Okay, I2R dash, the formula is I2R dash is equal to K into I2R. Okay, K into I2R. K into I2R. Have any doubts? You have any doubts, students? Students, you have any doubts? Any doubts? Have any doubts, students? Anyone? Anyone? When you're transferring the variables from rotor to stator, the notation which we are representing in rotor side is dash symbol. Okay, so this K is a transformer ratio. You have to divide the resistor reactance term by K square. Okay, K square. For resistance and reactance, okay, you have to divide the parameters by K square. For the current, you have to multiply it with K. Okay, you have to multiply it with K, where K is a transform ratio. It is defined as number of stator turns to number of rotor turns. Okay, number of stator turns to number of rotor turns. Have any doubts, students? You have any doubts? Any doubts in this equivalent circuit? Any doubts in this equivalent circuit? Any doubts in this equivalent circuit? Krishma? Shushma? Shushant?
No, sir.
Okay. Okay. Now can I continue to take a load test and a block rotor test? Okay. Load test and a block rotor test. Okay. Testing methods. Testing methods of induction motor. Okay, there are two testing methods are there. One is no load test, another one is blocked rotor test. Okay, these are the two testing methods. Okay, these two testing methods now we'll see in the PPT. Whether the screen is visible, PPT is visible. No load and block rotor test. Okay, see, this is the experimental setup in our laboratory. Okay, this is a motor, and here it will be spring balance. Okay, belt will be there. Here only it will be a regulator will be there to vary the regulator. Here belt arrangement. Okay, and this one, okay, this one we can say this is the brake drum load. Okay, brake drum, and this one will be the load. Okay, this is the load variable. Okay, load variable, and this is the belt. Okay, and this one will be the shaft. Okay, now when you release this load, what happened? The belt will be, it also be released, so it won't touch the drum, so automatically the motor will run very freely. Okay, it will run very smoothly. Okay, that concept is nothing but no load. Okay, during no load condition you should not apply any load, so the machine will be running in normal condition within synchronous speed. Okay, within synchronous speed 1500 rpm. That is the concept of no load. Okay, so this diagram will be the circuit diagram of no load test. Okay, so here a three-phase supply. Okay, this is the, here you see a box. Okay, here only we have to give a three-phase supply R, Y, B, and to measure the three-phase current we are having a 3 ammeters. Okay, we are having the 3 ammeters. Okay, so these 3 ammeters which will measure the parameters called I0. Okay, I0 will be the no load current of any phases. You can measure in R or Y or B. This is R, this is Y or B. Okay, now you are giving 230 volt. Okay, if you are giving 230 volt, in table we have to mention 230 volt. By using auto transformer you have to apply the voltage 230. If you give 230, when you give the 230 volt, you should not apply any load by using this condition. Okay, you should not apply load. So during that time the current value which we are measuring here, it will be 2 ampere. Okay, for 230 volt, 2 ampere. Okay, and when the current flowing in this stator winding, there will be a power has to be measured. So for that we are having 2 watt meters to measure the power. Okay, 1 watt meter for measuring the power in R to Y, another watt meter to measure the power from Y to B. So W1 plus W2. Okay, so this watt meters will be, it will be 20 watts or 220 20 plus 20. Okay, like that it will come. Okay, and the voltage also we can measure, that is the no load voltage 230 volt. Okay, the machine will be running. So when no load test will be taken in the laboratory, at that time we have to maintain NR equal to NS. Okay, NS value is already fixed at 1500 rpm by the manufacturer. Okay, NR should also be 1500 rpm, which is almost will be equal. Okay, that concept is nothing but no load test. Okay, so in no load test there are 3 ammeters we are using, and 1 voltmeter and 2 watt meters we are using it to measure the current, to measure the voltage, to measure the power. Okay, so to measure the voltage V0 we are using 1 voltmeter, that is V0. This is V0, and the no load current I0 and W0. The combination of W1 and W2 will be W0 equal to W1 plus W2. Okay, W2. Now how to find the calculations? W0, the formula W0 equal to root 3 V0 I0 cos phi 0. Okay, V0 I0 cos phi 0. Therefore the power factor cos phi 0 equal to W0 by root 3 V0 I0. Okay, this root 3 stands for the machine running in star connections. So in star the V line is equal to root 3 into V phase. Okay, that's what this root 3 into V0 is coming. Okay, this is in star. Okay, star for starting, delta for running, delta for running. Okay, and this is the equivalent circuit that I already explained. Okay, there are two components are there. Okay, when you are measuring the when you are calculating the rotor no load test, during the time there will be a two currents are flowing. One is active component current, another one is magnetizing component current. Active component we can use a symbol called IC or IW. Okay, magnetizing component you can use I mu or I M. Okay, these are the two symbols which will be using in stator side. Okay, these are the formula for active component. IC equal to I naught into cos phi naught in terms of power factor, but for magnetizing component I naught into sin phi naught. You see, only cos is applicable for active, sin is applicable for magnet, and for R naught equal to V by I, because we know the Ohm's law, V equal to I into R. So from that R equal to V by I, and X naught also V by Im. Okay, these are the formulas which will be using for no load test. Okay, these are the formulas we'll be using for no load test. This is my first formula, power factor formula, third one, fourth, and fifth formula is R naught, sixth formula will be X naught formula. Now in no load test, while performing the no load test, there are two losses are be produced. One is stator copper loss. Okay, the first loss will be stator copper loss. Okay, stator copper loss will be produced. Another one is stator copper loss. The second one will be friction loss, because when the machine is in running condition, definitely there will be a losses will be produced in mechanical sector. Okay, that is nothing but friction and windage losses. Okay, these are the two losses. We know the stator copper loss formula, 3 I naught square into R1. Okay, 3 I naught square into R1. Okay, this is the formula for stator copper loss, 3 I naught square into R1. Okay, this no load test will be very easy to measure the speed. Okay, in the laboratory, what we'll do, we have to apply the input by using the auto transformer. When you apply the voltage of 0 to 100, during that time the machine is running, the speed will be increasing, because you are increasing the voltage, right? 0 to 100, like that your speed is also be increased, but you have to maintain the speed till 1500 rpm. Okay, at that time you should not apply any load. That is nothing but no load test. Okay, no load test. The second test will be block rotor. These are the theory. Okay, just to go through it. Block rotor test. What I'm doing block rotor test here, this bolt, okay, this regulator, I have to make it tight. Okay, once you make it tight, the belt will be locked this drum. Okay, it will be locked, it will be touch the drum and it will be locked. During that time the motor not rotate. Okay, not rotate. So during that incident you have to apply the voltage. Okay, 0 to 100. Okay, first you have to apply the voltage, 100. Okay, 100 voltage you have to apply. You apply the load also, but the motor not running, so you have to measure the voltage and current. Okay, voltage and current. Understood or not? Okay, during block rotor test, first step, you should lock the rotors. Okay, you should lock the rotors. Okay, you should lock the load. So when you lock the load tightly, what happened, you have to apply the voltage, initial voltage you have to apply 0, 100 you have to apply. Once you apply the 100, okay, there will be a voltage we are calculating, current we are calculating, but the motor is locked, the motor not rotate. Then you have to apply 200. When you apply 200 also, you can measure the voltage and current, but Power also you can measure it, but the motor should not rotate. That concept is nothing but locked rotor test. Okay, so when you are taking a screw cage motor, here the rotor bars are permanently short circuited. Okay, permanently short circuited. When you take slip ring induction motor, the slip rings are short circuited. Okay, when you take the screw cage motor, the rotor bars are short circuited. Rotor bars are short circuited. When you take a slip ring motor, the rotor winding is short circuited through slip rings. That is a basic difference. If you take screw cage motor, the rotor bars are short circuited. If you take a slip ring rotor, slip rings are short circuited with the brushes. Now here the power WSC is equal to root 3 into VSC. VSC stands for short circuit voltage. Okay, VSC into ISC into cos phi SC. Okay, therefore cos phi SC power factor equal to WSC by root 3 VSC ISC. Okay, here also there will be a rotor copper loss will be produced. Okay, because the rotor is locked, right? So the losses will produce a rotor copper loss. So rotor copper loss formula 3 ISC square into RSC. Okay, RSC. Okay, RSC is the rotor resistance. Okay, rotor resistance. Okay, have any doubts in this? Have any doubts here? Any doubts? This concept is nothing but locked rotor test. Locked rotor test. This locked rotor test is performed under normal operating condition when the rotor current and frequency are on same conditions. Generally, in the locked rotor, the slip value will be ranging from 2 to 4%. So therefore, the resulting frequency is in the range 1 to 2 Hz. Stator frequency will be 50 Hz. Okay, these are the specifications. And here we can operate the motor from 1 kilowatt to 20 kilowatt. You can operate to test the block rotor test. Okay, any doubts? Any doubts? Students, you have any doubts?